Good afternoon, ladies and gentlemen. We'll just take a second to let people settle down. I'm Jan Soike, the SPA Space Physics and Aeronomy President, and it's my great pleasure today to be the introductee for our Van Allen speaker today. Our Van Allen speaker is Professor Daniel N. Baker. He hails from Iowa, and he received his early degrees in mathematics and physics, but in 1974 he received a PhD in space sciences, and his major professor was none other than our distinguished Professor James Van Allen. So the connection we have today is rather excellent. After his PhD work, he spent 3 years at Caltech as a research fellow. He then moved on to Los Alamos, where in the Space Plasma Physics Division, he was first a staff member and eventually a group leader. After that period of time, he went to Goddard Space Flight Center, where he was the laboratory chief for extraterrestrial physics. So that's a definite ladder of leadership as well as science that Dan has pursued. Currently, he's a professor of physics at the University of Colorado in Boulder, and the director of LASP, the Laboratory for Atmospheric and Space Physics. And he's held that position since 1994. As a researcher, he's been prolific. He has over 700 papers, editor of 8 books, and for most of us, he is a spokesman both for our space science and the social impacts. And of course, his title today reflects this particular aspect of his career. He's been recognized in both areas by many of our sister communities. He is a fellow of the American Geophysical Union. He's also a fellow of the American Association for the Advancement of Science. He is a member of the International Academy of Astronautics. He's also a member of the U.S. National Academy of Engineers. In 2007, back in the university environment at CU, he's awarded the Robert L. Stearns Award and Medal for Outstanding Research, Service, and Teaching. So he still is one of us. In 2010, AIAA awarded him the James A. Van Allen Space Environment Medal. So this link back to our predecessor here, the Van Allen, most certainly is running in Dan's blood. Most recently, on behalf of us all, he chaired the 2013-2022 Decadal Survey in Solar and Space Physics. He is a lead investigator on several NASA space missions, as you probably realize. The Messenger satellite to Mercury, the recent radiation belt storm probes, and magnetospheric multi-scale to come in the near future. Another facet of Professor Baker is that he cherishes the written word, not only for science society, but within our SPA community, as many of us can speak for. He's also famous for one-liners, and the little chuckle I hear gives it all away. So, unfortunately, I don't have time to do much with these one-liners, but Dan will be available later this evening to kind of fill them out. These one-liners yield phenomenal storytelling, and all I'll do is give you the one-liners and let you worry about them. So one of the first ones is, "We are going to die." Now, in the hands of most of us, it's fairly normal, but Dan is special, okay? The next one I have here is, "I learned that I have a second gear." Okay, Dan? I don't know. A third one I have is, "I don't eat anything with a brain bigger than a fish." Okay. The final one is the one I'm familiar with personally. The comment, out of context, is miserable, but it's a giant among men. Okay, without further ado, it's my great pleasure to invite Professor Daniel Baker to step up and deliver the 2012 Van Allen Lecture. And it's up on the screen, Magnetospheric Exploration, and the specific attributes that he wants to talk about today, if I can read my own writing. Basic research with a high public purpose.
Thank you very much, Jan. Thank you all for being here. It's a great honor and privilege to be able to speak in the Van Allen lecture series. I'm going to talk today about basic research, but also research that has applicability to a societal need. And this is one of, I guess, the most iconic image of the space era. Here you see Professor Van Allen, and you see Wernher von Braun and William Pickering, and holding aloft the engineering model of the Explorer 1 spacecraft. And because of the association with Professor Van Allen, I had the privilege of meeting Wernher von Braun before his death when he was at NASA, and later at Caltech to meet William Pickering. And I think in many ways the association, the early association with Dr. Van Allen has opened so many doors for me, and I am delighted. While I was still an undergraduate, actually, I guess I had done well in a class that Tom Kermegis was teaching, modern physics, and I was hired to work in the physics department. And while still an undergraduate, Dr. Van Allen came and asked if I would be interested in working on a mission that was going to Jupiter and beyond, and whether I could help design an instrument that could measure low, I guess I should say medium energy particles in the presence of what would be possibly huge background fluxes. And I was, of course, delighted to say yes to that. And a paper that I think came out in '76 was sort of our definitive look at this. And so we were able to measure down to a few tens of kilovolts using a scatter geometry in the presence of these heroic fluxes of extraordinarily high energy particles in the Jovian system. This remarkable thing that a professor of Van Allen stature would invite students to play such key roles was, of course, one of his characteristics, and it stayed with me throughout my life and career. And at Colorado now, we have over 100 undergraduates working in our lab on all kinds of hands-on kind of science projects, and over 70 graduate students. And so I think that this has been maybe one of the best influences, as far as I'm concerned, of the early years. In 1985, Stuart Gilmore and John Spreiter organized a session under the auspices of the AGU history section to have a special session and a book about the discovery of the magnetosphere. Dr. Van Allen was supposed to be one of the speakers. He had to bow out last minute, and Carl McElwain, seen here, stepped in to fill in with a talk there. But I was actually asked to give a talk looking more toward the future opportunities in magnetospheric research. And it was a delight then to be on the same stage with Jim Dungy, Bob Helliwell, Alex Dessler. Here's John, Shinaka Sofu, and Carl. And one of the great things out of this was the book chapters. And Dr. Van Allen had a chapter, and there was a part of this that I just found delightful. And I'll quote this from the this, of course, is the famous Time magazine cover resulting from the early radiation belt work. He said, following our 1 May report and news conference, we received many inquiries for further details. One that lingers in my memory is the following telephone conversation. Quote, this is John Lear, science editor of the Saturday Review of Literature, calling from New York. Heavy emphasis on calling from New York. Then a long pause, waiting for me to recover from the thrill of hearing from such an important person in New York, no less. Actually, I did know who he was, and had often characterized him as the anti-science editor of the Saturday Review. He continued, I read of your recent report of the discovery of radiation belts of the Earth and thought that I would do a piece on this subject. What I found remarkable was that such important work had been done at a Midwestern State University. Heavy emphasis on Midwestern State University. Well, I don't think that I responded with any actual profanity, but I did manage to convey a suggestion as to what he could do with his piece, and hung up. The next day, the president of my university, Virgil M. Hansher, called me to report that Mr. Lear had called him to complain about my discourtesy. I then gave a brief explanation of my reaction, at the end of which Hansher replied, I promised Lear that I would call you, and you may now consider that I've done so. By the way, Van, my congratulations. I never heard from the matter again. It's great to have a boss like that. Well, you know, this anecdote really characterized. I think that Dr. Van Allen was always maintained modesty, but he also had a fierce pride, and in his sense of humor was great. I remember in one instance with a reporter in my presence, he said, the reporter asked, Dr. Van Allen, what are the Van Allen belts good for? And he said, well, they hold up Van Allen's pants. And pretty good response. And, you know, in another instance, it was at a planetary encounter. We came back, a small group had gone out to dinner. We came back, and all the reporters wanted to talk to the famous Dr. Van Allen. And the reporter said, Dr. Van Allen, what do you have to say on this auspicious occasion? He said, well, I just had a great pizza. And so the reporters were rather taken aback by that kind of thing. It was also a great privilege later on in 2004 to be at an event, I think largely organized by Don Gurnett and his colleagues at the University of Iowa, but to be able to celebrate the 90th birthday of Dr. Van Allen. And here you see him, Mrs. Van Allen, and their son Peter right here. And Peter will figure in a second what I'm going to say. But I was asked by Don to give an after-dinner kind of talk that would mix some science and also mix maybe a little bit of humor. It was easier to talk sort of about the science than the humor part, I suppose. But I was delighted to be there, again, with Tom Cremegis, who's been such a great friend and advocate over time, Ed Stone, my mentor after Iowa at Caltech, Dr. and Mrs. Van Allen. But at any rate, I decided to intersperse in my talk a little bit of humor. So I thought, well, why not go with a David Letterman kind of top 10 list? I won't trouble you with all of the one-liners here. Some of them are not worthy of repeating. Probably all of them are not worthy of repeating. But anyway, just to give you a flavor, number 10 was communication satellite disruptions prevent C-SPAN from showing Congress at work. No one notices. I got down to number 6. Pipeline corrosion interrupts flow of Dick Cheney's retirement funds from Iraq. Number 5, solar particles caused George W. Bush to lose all judgment. Stars in a really bad TV movie called Solar Flare 2004. Then went on, number 3 was increased atmospheric drag brings down Air Force One, leading to mission accomplished aircraft carrier landing. And finally, I don't know if Grunsfeld's here, but number 1, astronauts go berserk in zero-gravity pie-eating contest. At any rate, I thought these were sort of funny at the time. And Peter, I was talking to Peter Van Allen after the talk, and he said he liked it, but did I know that his dad was a staunch Republican, and I would probably be hearing from him about some of my remarks. And sure enough, on the 18th of November, a letter dated the 18th of November, Dear Dan, many thanks for your attendance at my 90th birthday party, and especially for your appropriate and informative after-dinner talk. And then he goes on to say some nice things, recollections about involvements we had. He also notes that much of his work was really space weather related. And then the PS is, also I enjoyed the lighter moments in your talk, including your, let's see, your top 10 letter mania, but some of your items may need a little work. And so So indeed, the political came to bite me again. At any rate, I take very strongly the point that he makes here about his work being very analogous to some of the things that we are still doing today. If you look at the understanding of magnetospheres, there's a scientific branch that we often talk about, understanding the basic processes of magnetospheric acceleration and transport. But there's also the applied part of this. It affects humans in space, satellite systems, power systems, and even possibly affecting climate change. And so these two branches are, I think, supportive of one another, important to one another in many different ways. I know when I went to Caltech, there was a very heavy emphasis in Ed's group in understanding solar particles, acceleration of the sun, understanding the radiation environments of all the planets, as with Voyager, the extension of these cosmic understandings to other objects like the Crab Nebula, and later work that I did at Los Alamos, even in studying particle acceleration and transport in extragalactic jets. But in all these cases, it's really the energetic particles, often energetic electrons, and strong magnetic fields that make these visible. But when I went to Los Alamos, I was given access and major responsibility for using data from our operational satellites. And this was, I thought, a marvelous opportunity, and one that showed me over and over again that good service can also lead to good science. And studying these data sets and being able to use them to both understand the processes and then to apply that for the folks who really needed to make these systems work in space was quite important. The energetic particle, charged particle analyzer sensors, as I was talking about, measured with remarkable sensitivity the energetic particles there, showed some fascinating features where lower energy particles were closely related to the external driving. I was privileged at that time to be in a group with great solar wind experts like Jack Gosling and Bill Feldman, and to be able to see that there were different processes that were affecting the lower energy and higher energy particles, and to begin to understand how the solar drivers, the solar wind drivers, can lead ultimately to the acceleration. So we have this powerful accelerator just a few hundred miles, few thousand miles above our heads, operating in the Van Allen regions, but really being driven by the external forcing from the sun and the solar wind. And this was really quite intriguing. Of course, it began to be formulated sort of in those days back in the 80s, the term that eventually became so synonymous with our field space weather. But understanding that, and this is probably the most recent variant of this definition from the National Space Weather Program Plan, but understanding that space weather affects all kinds of spaceborne and ground-based systems, can endanger life and health in many ways, and can cause this panoply of effects. And so space weather has been, let's say, crystallizing more and more as to what it is and what it means to society. At Los Alamos, for example, we were asked to take sensors that had other purposes and sort of adapt them to be more efficient and effective at measuring the space environment. And the one that was born from that kind of need was the spectrometer for energetic electrons, C, and it was one of the first sensors that was really capable of making these measurements up to quite high energy in this hostile space environment. And using the sensors there to look at the relationship, every one of these vertical arrows is a time when the spacecraft was suffering from anomalous behavior in the star tracker system, which of course disrupts the whole operation of the satellite. And every one of those was associated with bursts of very high energy electrons that this C sensor was able to observe. So again, good service to help the operations, but to get good science out of that as well. We began to apply the measurements at geostationary orbit to other satellite systems that were having problems. In this case, the NOAA-GOES satellite failure or operational problem occurred, and we were able to see that this had been preceded again by a long period of very high energy electron behavior, we made these measurements over very long periods of time. These operational satellites operate for years and years and are replaced regularly. So we were able to see long solar cycle changes and 27-day periodicities, again associated with solar wind streams, quite intriguing. Began to realize that there was this whole swarm of spacecraft out there that needed to know more about the space environment, and that we could use these measurements to help support both commercial and military systems. So that I thought was very beneficial. When I went to NASA Goddard in '87, I had lunch with the late Frank McDonald, and I later learned that Frank never just wanted to have lunch, he wanted to talk about something, and he asked me what I thought of small satellites, and I said I thought they were great. He said, well, good, you'll be the project scientist for the Small Explorer program then. And so Len Fisk and others had been getting this program, SMEX program, going. It was one of the best management experiences I think I've had, and to be part of the first selected one, the SAMPEX mission, Solar Anomalous Magnetospheric Particle Explorer. We had a brief but I thought very good session this morning talking about SAMPEX, about its role in understanding the origin and nature of anomalous cosmic rays, of solar energetic particles precipitating over the Earth's poles, of mapping the radiation belts, at least in the far field, at the low end of the field lines, and even looking at atmospheric coupling. But this small spacecraft that was quite inexpensive but performed remarkably and has returned information about magnetospheric processes that I don't think we would have really dreamt of when we started that program so long ago. Of course, about the time SAMPEX was launched, we were entering into a time of very high energy, high fluxes of very energetic electrons in the Earth's magnetosphere. Satellite failures such as the ANIC, the Canadian ANIC satellite failures, needed to be analyzed. And so we started to use the SAMPEX mission as a monitor to just look at what were the associations. And these ANIC and Intelsat failures occurred in January 1994. The external solar wind data helped to show the usual pattern. This high-speed streams occur, the high-energy electrons increase. These had been high for a week or so, and the satellite failures occurred. And this is over and over again, we were able to see this pattern where we could more or less assure that when high-energy electron enhancements were occurring in the magnetosphere, they could cause a phenomenon called deep dielectric charging. That's illustrated here, where these high-energy electrons, which can punch through very thick shielding, can bury themselves in dielectric material. If they build up enough, it can lead to an electrostatic discharge that can do immense harm to satellites. SAMPEX was launched in '92, continued to operate into the early 2000s officially, and there was, of course, the famous Halloween storms. But this is the long run here from a Nature paper about this Halloween storm event. But you can see the relationship to the sunspot number, to the solar wind speed, and this Halloween storm completely rearranged the magnetosphere, drove the radiation belts into quite a different state, and led to a filling of the slot region between the inner and outer Van Allen belts, and dramatically enhanced the inner zone and caused, again, a whole bunch of satellite operational problems and anomalies. But this Halloween storm really drove home to me, in my mind at least, the tools that we now are getting to look at the sun. These are SOHO images from the EIT and from the coronagraph, and to be able to see the flare, then to be able to subsequently see the halo coronal mass ejection that results from this. The snow in here is the very energetic particles that resulted from this disturbance. And to be able to see sort of these prototypical drivers from the sun and to measure the response at the Earth was a very important feature. This diagram or this animation has been shown again and again and again, but I think it sort of illustrates the prototypical event we kind of worry about of a coronal mass ejection, a powerful coronal mass ejection being released, then moving outward in front of it, the shock wave in front of it accelerating particles further, leading to some of the effects you saw, and then ultimately, if the interplanetary field direction is right, a powerful interaction with the Earth's magnetosphere leading to great gating, and essentially some more energy enters the system, and leading ultimately to powerful disturbances, not only in the magnetosphere itself, but down into the ionosphere and down to the very surface of the Earth in many real respects. And so these kinds of things got me much more interested in policy kinds of implications of space weather. I think it was at a luncheon at the Space Weather Week in 2007 with Ernie Hildner and Rich Benke and probably Dick Fisher, talking about, we really ought to have an assessment of what are the societal and economic impacts of severe space weather. What's it really costing our nation? And so under the aegis of the National Academies, put together a group to organize a workshop to look at the econometric analysis of space weather. We had representatives from many of the different affected industries, put together a group that ultimately wrote this report. And this report was published at the end of 2008, has been translated into other languages. The most recent version I've seen was in Chinese. But it's continued, I think, to be an influential report which began at least this process of looking at what does space weather really mean, what does it cost society. One of the most used figures from that actually came from the Department of Homeland Security, but it really spoke about the effects of space weather on the electric power grid, a cornerstone technology for sure. And this diagram attempts to show that the interconnectedness, in a sense, of society, that if electric power goes out, not long before it affects transportation, emergency services, government services, banking, finance, potable water, fuel supplies. And I think it was George Sisko who had this term of the Earth being surrounded by a cyber-electric cocoon, and this report drove home that point quite strongly. And I think recent events have just borne this out further. And one of the headlines, trying not to be Chicken Little about all these things, but one of the headlines about these low-frequency, high-consequence events was that we as a society are becoming increasingly vulnerable to the effects of space weather, and that under the right circumstances, a Carrington kind of event could cause trillions of dollars of damage and lead to outages for literally for many years. And so this is gaining increased attention with policymakers, and as part of the duality of our field, that we can understand the basic physical underpinnings, but we can also understand and help to inform policymakers about these societal consequences. Also in this NRC report was looking again at the spacecraft effects. This is a diagram in the report that was put together by Mike Boudreau, who was at this meeting at least earlier this week. And Mike works in the aerospace engineering arena, and using his databases looked at the serious operational anomalies. And here you can see that this one powerful set of storms in the Halloween period dramatically increased the number of events and failures. And this, again, shows that all it takes is one immensely powerful space weather event to wreak tremendous havoc. So I think it was thinking along the lines of the work of the 80s and so on, work of many people, really. And I know Lou Lanzarotti's in the audience. The kind of thinking that he brought from combining industry and government concerns really led to the development about a decade ago of NASA's program, NASA's involvement in space weather, embracing of space weather in the Living with a Star program. And this really had the goal to sort of use NASA's capabilities to study the connected Sun-Earth system. And of course, we now see SDO operating to observe the sun, but part of the program was to also look at the geospace end of things. And so a science definition report came out advocating for radiation belt storm probes component to study the acceleration and loss of radiation belt electrons, to understand the creation of new belts, and quantify effects, look at the seed particle question, and to develop specification and forecast models. And so this program got underway, and we were delighted to be part of this. I was delighted to be a lead investigator on one of the components of the ECT suite on board the radiation belt storm probes. And this is the instrument that I have charge of, and work with our team of engineers and managers at the Laboratory for Atmospheric and Space Physics to develop this new instrument. It is a husky instrument, very well shielded. Its goal is to measure the highest of the energy electrons in the radiation belts, and to also be able to measure the protons in the inner Van Allen zone. This utilizes passivated silicon solid-state detectors from Micron Semiconductor Limited, stacks these in a telescope arrangement, as you saw in the previous diagram, tries to shield the entire structure sufficiently to beat down backgrounds. And working with my colleague now at Goddard, Sri Conical, we went through very detailed Geont 4 modeling of our designs in order to try to optimize the design. And so here we have the stack of paired detectors, 9 double detectors in all, surrounded by heroic amounts of tungsten and aluminum shielding, putting a beryllium window in the front to beat down the low energy particles that are coming into the stack, careful design of the collimator, and then using Geont to blast this design with, in this case, 10 MeV electrons coming in through the collimator, and showing how the larger back detectors help to collect and retain a lot of the energy that's coming into the whole detector stack. And so in order to understand this, we had experience from Sampex, from CRESS back in 20 plus years ago, and we sort of knew what we were going to have to cope with. And some of the spectra here show the models that we might expect, also some of the most extreme cases that CRESS saw. And the blue was sort of the assigned requirement range for the REPT instrument. And we saw that we had to have a large dynamic range, probably deal commonly with 6 orders of magnitude variation in particle flux, so we needed a tailored dynamic range. Had to have the sensitivity to measure quite low fluxes in the slot region between the inner and outer Van Allen zone, to also be able to have very fast electronics in order to minimize dead time for the most intense events. We had to reduce low energy pileup, and hence the beryllium window, to keep out the lower energy ones that could confound the higher energy measurements. We wanted to reduce chance coincidences in every way we could, again with fast electronics if possible, and to have the right kind of sandwich design of shielding to really beat down the bremsstrahlung production. And we knew, again, from old models, roughly what we would be dealing with. This is phase-space density versus L, radial distance, effectively. We knew that this might be the nominal kind of behavior, but we knew that acceleration events, largely due to radial diffusion, would probably drive up the intensity of electrons in the middle range here by quite some amount, but that the local heating due to interaction with chorus waves and other waves would also lead to quite a distinctively different radial profile. And in order to measure these and distinguish between these different models, we would have to have very certain, that is, we'd have to beat down the uncertainty in our measurements quite considerably. And if the uncertainty became too large, these things would wash together and we'd have no chance of really sorting out the observational facts. So these are the pictures of the 2 flight units on either side here, the engineering model, which is still back in our lab and available for testing and evaluation of issues. But these were beautiful instruments, in my opinion, were integrated onto the spacecraft, and very successfully integrated, I might say. And on the 30th of August, we had a beautiful, we had an aborted launch. We had, after a couple of false starts, the spacecraft were launched on an Atlas V vehicle. The spacecraft themselves were developed very effectively by a great team of people at the Applied Physics Laboratory. The launch was about 4 o'clock in the morning, a spectacular night launch, and got a great ride on the Atlas vehicle into the planned, essentially a geostationary transfer orbit. The spacecraft were deployed, antennas and other things started to deploy almost immediately. The orbit, as I say, was a highly elliptical one moving through the inner magnetic field region. And here you see a portrayal then of the radiation belt structures, the inner and outer zone, as we expected and hoped to see. And the two spacecraft starting out close to one another and then moving further apart and actually pacing and lapping each other. And then the two spacecraft were expected to go through a 60-day commissioning phase and then would be ready for the operational phase, expected to be 2 years at least. We were supposed to turn on the REPT instruments over a month after the launch, but we knew that the SAMPEX mission was on its last legs. It was going to be, due to atmospheric drag to an active sun, was going to re-enter the atmosphere sometime between August and December of 2012. And so I think I was probably the first one who started to beat the drum, but the whole project, everybody got on board for the idea of let's get the instruments, especially the particle instruments, so we can compare with SAMPEX, turned on as soon as we could. And we were able to do that. So on essentially the second day after launch, we got the first REPT instrument turned on, and we turned on the second one about 12 hours later. And fortunately we did that because SAMPEX re-entered on the 13th of November, and so we have about 2.5 months of overlap between the low-altitude measurements from SAMPEX and the high-altitude measurements from RBSP. On the 9th of November, the RBSP spacecraft were renamed the Van Allen probes mission, and so this is another great honor for Dr. Van Allen, and an honor, I think, for all of us to be able to work on it. So, sort of first light data from SAMPEX, from the REPT instrument are shown here. We turned on about midday on the 1st of September. And here you see energy time spectrogram from the REPT A instrument, line plots of those channels. These are using the pre-launch loaded tables for responses. Here are the high-energy protons, measuring protons from about 15 MeV to well over 100 MeV. And again, the line plot, seeing distinctively the inner zone protons and the very powerful outer belt variability. This is from the 5th of September, I believe, and is showing now more detailed information, one sort of orbital pass for the REPT A instrument again at a particular energy. I think these are about 3 MeV or so, probably 4 MeV electrons. And this is the roll angle. So we have 10-degree angular sectors. And here we see played out before our eyes the trapped kind of electron distributions, where here is the magnetic field direction along here and here. The intensities are much higher perpendicular to the magnetic field than parallel. Here we fly through the slot region and into the inner zone. And then we fly below the Van Allen belts entirely, and it's the cleanest, the most quiet data you can imagine. Hardly a single count in there, so we're just delighted with the performance all in all. So stepping back and taking a longer view, we started on the 1st of September, turned on, and so this overplots the REPT A measurements and the REPT B measurements for 4 to 5 MeV electrons. We have better energy range, better energy resolution, 25% delta E over E, better time resolution, better everything on this mission than we ever have had before in the radiation belts. And when we first came on, we were blessed by the sun to have driven a powerful acceleration event where the electron intensities were extending up well above 10 MeV. We see the inner zone, the slot region, the outer zone electrons, sort of what we'd expect, but as I say, just a very intense event. However, very quickly, something came along to knock down the flux of much of the outer zone. We're then left with a feature. I was reading about the CERN accelerator, and I had storage rings on my mind, and so I've dubbed this the relativistic electron storage ring. But here, my first thought was, geez, this is so steady and rock solid and just there all the time. There must be something wrong with the instrument. But then both instruments showed exactly the same thing, so it didn't seem very plausible. But what we subsequently saw was that the outer Van Allen belt started to show all kinds of variability. This just stayed there. And so we went from having not 2 belts, but 3 belts, 2 slot regions, and at least for those of us who looked for 20 years at other kind of radiation belt data, this was very striking. So this is a bit longer period of time, a run of time. This shows the 2 to 2.5 MeV channel up here, the 4 to 5, the approximately 7 MeV electrons, and each of them arrayed in this radial distance versus time format with the color coding shown by this bar. At the lower energies, the ones we're sort of more normally used to, this third belt feature is not quite so obvious, but as you go to the higher and higher energies, it just stands out immensely clearly. And then this persisted for about 4 weeks, and then it was just shut off almost like a knife edge. I'm now going to show you an animated GIF. So we've taken all the data from the 2 instruments in this 4 to 5 MeV range, laying it down on a meridional plane projection. So obviously here's the Earth. This is radial distance again, L, and magnetic latitude. And what you see at any one time is about 3 days worth of data displayed. Old orbits are removed, new orbits are added on, and now you can see this 3-belt structure played out. The inner zone, tightly confined toward the equator, very stable with time. The slot region, normal one that we expect, very well seen with time. The outer part of the outer Van Allen zone changing dramatically from day to day and week to week. But then eventually, here we're coming toward the end of the month of September, and now the entire outer belt is virtually annihilated. And maybe I could play that if I went backwards, but I think I will show you some stills instead of this. Again, these are sort of 3-day groupings from the first turn on, seeing the 2-belt structure, seeing the erosion of the outer part of this, leaving just this storage ring feature, and then that persisting rock solid for several weeks, and then the outer belt showing all kinds of dynamics, and then eventually the whole thing just kind of disappearing. So this is a very busy slide, but an annotation which now shows the external solar wind drivers, the solar wind speed, the interplanetary magnetic field properties, the geomagnetic indices, the DST. And I just have to say what a great job the entire Van Allen Probe's team. I will especially want to thank our colleagues at the Science Operations Center at Los Alamos. Mike Henderson has done a heroic job in getting analysis of all this stuff together. And for us to be able to go from sort of raw data to very refined kind of level 3 comparisons in such a short time is just astonishing to me. On this plot is also the modeled location of the plasma pause, the outer extent of the colder plasma surrounding the Earth, and from Jerry Goldstein at Southwest. And so this picture plays out all the things I've been telling you about. The 2-belt structure initially, the plasma pause being quite close to the Earth, and all of this happening outside where the chorus waves could really interact with these particles, accelerate them probably. And then the plasma pause moving out to a place where all of this stuff going on or not going on inside, the whole storage ring is protected from the external drivers and from the wave actions, and so it just slowly dies away. And then, again, a powerful shock wave comes along at this point and leads to a powerful geomagnetic storm, but also is what shuts down this outer radiation belt almost entirely. And then it's very quiet for a period of time. A new set of drivers comes along, again, a wipeout, and then a reacceleration of the outer belts. I don't think we had any right to expect the sun to be so cooperative for us in the first month or so. If we hadn't been driven by the SAMPEC's demise or imminent demise to turn on our instrument on the second day, we would have missed all of this. And in my experience, at least, I never expected to see this degree of spatial structure or this degree of variability in such a compact form. And so we are, I think, blessed in many ways to have been able to get such an early look and such an interesting look at such a fascinating dynamic system as operates in this region above our heads. And so this is a schematic diagram that purports to tell some of the essential elements of this story, which is that the normal, the expected structure, the part of the lore for the last 50 years is that there are two belts, an inner zone, a slot region, and an outer zone. The slot region largely determined by the waves that are related to the plasmaspheric structure. But what we saw for this exceptional period of time is really three belts, two slots, and we're now scratching our heads and puzzling about this, and I think it's going to be fascinating to study the underlying science for this set of observations, and many more to come, we hope. So let me begin to wrap up here and just say that we are in a very special time to be able to look at the sun in the ways that we can, to see the active drivers of the connected Sun-Earth system, to understand the forcing of the near-Earth system, to understand also how that forcing can lead to powerful effects in technological systems is really quite remarkable. We know from the many observations in recent missions that this placid, stable, very laminar kind of picture of the magnetosphere that we've had in our minds is very far from the truth. It's a much more dynamic and much more vigorous system, but that these changes really affect continental scale power grids, pipelines, can lead to serious societal consequences, and it's happened before, and it's only a matter of time until it happens again. And of course, that this can affect in very notable ways ground-to-ground communication, can also affect the operation on aircraft, and of course satellite-to-ground communication can be severely disrupted. And we now have many more systems like dependence of financial systems, the global positioning satellites, and many others that depend on working through. This affects precision agriculture, navigation at sea. All the things we know are part of the space weather story. And then, of course, the effects on individual spacecraft and entire constellations of spacecraft. And some of the things we've talked about here, the charged particles that I've tried to talk to you about, can affect solar cells, solar panels, and ultimately can affect humans on the space station and if we travel outside the protective envelope of the Earth. And we've built a lot of this capability on the back of these wonderful scientific satellites that we're all privileged to be part of. So I come back to where I started with a picture of Professor Van Allen. This is the way I remember seeing him many times, at least, was sitting at his desk in Van Allen Hall, surrounded by big stacks of computer printout, and working on analysis of data, tracking not only the behavior around the Earth, but with the spacecraft that are out at the fringes of the system as well. And it's indeed a privilege to have known him and to have worked with him, and I think he was a great teacher, a great mentor, and I, for one, appreciate very much the chance to have worked with him and to be here to talk about some of that today. So let me conclude by saying that I think the challenges of space weather really affect all developed countries. They affect civilian military systems of all stripes. And I think that work on space weather specification, modeling, forecasting really has substantial societal benefit. And it truly is, I think, basic research with a high public purpose. I think it's fascinating and quite gratifying, really, to be able to pursue this basic research that also has possible important applied components. And I think it's one of the special things about our discipline of solar and space physics that we have this duality, that we can really both do local astrophysics and also do things that are genuinely useful to the society of which we're part. And I think that future space exploration, whether human or robotic, and certainly most modern human endeavors, will require that we have further major advances in the physical understanding of the system, improved transition of space research to operations. And I sincerely hope that Dr. Van Allen would be pleased with the continuing work to advance this relevant work. And I think he'd be particularly pleased to know that the strong basic research underpinnings as well are represented in the Van Allen probe's mission. So thank you very much.
Before we open the floor for a few questions and some answers, I'd like to award our speaker today, Daniel Baker, an AGU certificate. This momentous occasion. I believe Dan will take a few questions if anybody has a question or a comment.
Especially easy questions.
Oh, there is one at the back.
Yeah. Yeah, well, I think that's a great question. And, you know, the integrated effect of smaller kind of phenomena, I think is more appreciated all the time. I know Carl Schreiber's been working on some of those things, for example. And it may well turn out that just the relentless beat of these smaller things ultimately may have more effect on, integrated effect on technological systems. I don't think we really know that. I think as humans we're sort of naturally drawn to the most extreme kind of events, and we tend to focus a lot of our attention on that. But obviously the more frequently occurring and possibly the more long-term degradation of systems by this relentless beat of smaller space weather features may be comparable. I have to tell you, though, that like a powerful hurricane or like a powerful flood or other events, it certainly gets one's attention when a huge event occurs. And I was particularly drawn myself to an event that occurred in July of this past year, which only hit stereo A. It didn't come toward the Earth. But some of the analysis that's gone on, if we can reconstruct what the solar wind speed was for that event, suggests that if that event had hit the Earth, we would have probably been looking at a DST of something like 650 or 700 nanotesla, which is much larger than anything we saw in the 20th century. If that had hit the Earth, I think we'd have been talking about a Carrington kind of episode. And again, that would happen with such immense sudden impact. I think that again, policymakers would be really pointing a lot of fingers at a lot of us about those kinds of events.
Dan, that was a wonderful presentation. I think probably the answer to this question will be just a simple yes or no, but here it is. In all your dealings with space weather and the decadal survey and all that, did anyone ever confide in you from the national security arena
Yes or no? I think you can infer from the fact that security folks spend a lot of money worrying about these kinds of things, both trying to make their systems immune and also trying to understand the consequences of the most severe events, that this affects, as I said in my concluding remarks, I think it affects both military and civilian systems. I also remarked the other day in a press conference that everything in space is a particle detector whether it wants to be or not. and so it's almost inescapable that anything you send into space is really going to be sort of clobbered by things. And so, yes, I think that you can infer that affects many systems I can't talk too much about. Okay.
I think we'll thank Dan one more time for the excellent talk he did.